There you go. So for partial derivatives, so we will use find and use these partial derivatives for functions of two variables, three variables. Find higher order partial derivatives. Actually, maybe the second, the third, and then we're going to look at pretty cool theorems about these partial derivatives. Well, so again, partial differentiation is about finding the derivative of a function with respect to one independent variable at a time while holding the other two variables constant. Well, we have different notations for partial derivatives. Well, back in Calculus 1, you learn about dy dx. Well, initially that was just a one symbol to denote the change of the dependent variable y with respect to the independent variable x. So, and then, well, if you apply this to a physical situation or another situation, well, you just change the letters, just making sure that you had the correct order for the dependent and independent variable. All right? This was called the Leibniz notation. So that's the Leibniz notation. And then you also learn about, what was the other one? Y prime, F prime. These are called Lagrangian notation. So now you're going to learn a new symbol for partial derivatives. So you have this like curly D. It's a curve, like a curve. It's like the number 2, but without finishing the number 2 like this. That's how it looks like. And that one has a special notation that's called Jacobian notation. That's because, well, the first mathematician who introduced this notation to distinguish an ordinary derivative, that is for a single variable function, from a partial derivative, that is for a function of multiple variables. That was after the mathematician Carl Gustav Jacobi. I don't know, Jacob Jacobi, right? So that's why we call it the Jacobi's D, right? It's a special symbol. It's not the regular D. Well, let's find partial derivatives, but before doing that, let's do some prep, okay? So y equals to 3x squared versus y equals to 3 plus x squared. All right, let's find the derivative of y equals to 3x squared. What's the derivative of y equals to 3x squared? Okay, so this is what you would do. Multiply by the old exponent, 2 times 3x, and subtract 1 from the exponent, right? 2 times 3 equals to 6, 2 minus 1. That's x to the first, which is just x. In comparison with the second function, 3 plus x squared, what's the derivative of 3?
0.
What's the derivative of x squared?
2x.
So y prime equals to 0 plus x squared, which is x squared. Where are we going with this? Because, well, now we're going to find partial derivatives. That is, the partial derivative of z with respect x. What are we going to do? We're going to treat x as our variable, and the other variable, which in this case will be y, that will be held constant this time. Yes?
Wouldn't that derivative be 2x?
Which one? Oh, this one. Yeah. Yes, that's a 2. All right? Thank you. I don't know what happened here. All right. So let's differentiate this function with respect to x. So here it is. So the derivative, let me add one more term actually, plus, I should have added this term, 5y squared. All right? Okay. So, what is the derivative of 3x with respect to x?
3.
3, okay, so that's 3. Now be careful here. What is going to be the derivative of x squared, y squared? Well, so in this case, the y squared, it's multiplying with the variable x squared in a similar way that the 3, it's multiplying with x squared right here. So since y squared, it's just a multiple constant while we're differentiate with respect to x, well, so we just differentiate the x, that's 2x, and keep the y squared as a multiple constant. All right? Next term, the derivative of 2x cubed y. Well, again, the y is multiplying. That's going to remain there, multiplying with the variable x. But we differentiate the 2x cubed, which is 3 times 2. That equals to 6x squared. Keep the y. Now, what is the derivative of 5y squared? This time we're differentiating with respect x. So the y variable is going to be held constant. The derivative of a constant, 0. Okay, so we're done actually. We're done. Now let's find the partial derivative with respect to y. Partial derivative of z with respect to y, that equals, what's that? Okay, so the derivative of 3x, well, so since this time we are holding x as our constant, we just focus on differentiating the y's, everything else remains constant. So 3x is a constant with respect to y, so that's going to be 0. Okay, now the minus, in this case, the derivative of x squared, y squared, well, x squared this time is going to be a multiple constant for y squared, so we differentiate the y squared, that is going to give us 2x squared y. All right. For the third term, 2x cubed y. So in this case, 2x cubed is just a coefficient. It's just a constant. Yes, there's a variable x, but it's multiplying and it's constant because the x variable is constant with respect to y. So we only need to differentiate y, which is 1. 1 times the coefficient, 2x cubed. And in this case, the derivative of 5y squared, yes, because we're differentiating with respect to y, we're going to use the general power rule, 10y. It's not 0 like in the other case. So 2 different results. That's because of the nature of the function, we are differentiating with respect to x, we're differentiating with respect to y. Okay. Example number 2. Now, how do we, so this is about finding more partial derivatives, but not just that. We will also evaluate these derivatives at a point this time. Not just as a value like we did back in Calculus 1, for instance, when we took the derivative of a function, recall that the geometric meaning of the derivative is the slope of the tangent line at a given point, for instance, at x equals to 5, at x equals to 7, your favorite number. Of course, as long as that number, as the function is defined at that value. All right? That's, those are the conditions that we need to make sure they're satisfied. Well, so in this case, we're not going to evaluate at one single point. One single value. We're evaluating the derivative at an order pair because we have 2 variables, or 3, that'll be an order triplet, or if we have an order quadruple, at an order quadruple for a function of 4 variables, and so on and so on. Just repeat this for as many variables as you have in your function. All right. So let's find the partial derivative with respect to x. So the partial of z with respect x. So here, differentiating with respect to x, notice how we have a product of 2 functions that contain x. So we will have to use the product rule. All right? So for the product rule, let me recall what the product rule looks like. U times v prime. That's u prime v plus v prime u. Okay? And that'll be, what's that? The derivative of x, that is 1 times the exponential e to the x squared y plus the derivative of the exponential, which, number 1, the derivative of an exponential is itself e to the x squared y. And in this case, we need a mini chain rule. We need to differentiate the exponent x squared y with respect x. So in this case, with respect x, we differentiate the x squared. That'll be a 2x, but in this case, the y, it's multiplying, so that'll remain constant, multiplying with the 2xy. All right, that times the u, which is x. Okay, let me just label so you can see what we're doing here. So that is u prime v All this madness here is v prime, and this x is u. So you can see the product rule in action for this exercise. And we're done. We're essentially done. Let's just clean up. So that equals e to the x squared y plus 2x squared y e to the x squared y. So that is our partial derivative with respect x. Okay, so yes.
Would you want to factor out the e to the x squared y?
You know what? I think it would be a good idea because we will later evaluate at a point. Yep. So, and that's going to reduce the number of substitution calculations, you know? So that's a good idea. E to the x squared y times 1 plus 2x squared y. Yep, much better. Good call. All right, so that's the first partial derivative with respect x. So should we, yes.
Why is it 2x squared y? Shouldn't it be 2x y?
Which one? This guy?
Yeah.
Yeah, but this x times x, it's x squared. And well, here there's only a 1. So the only common factor is that exponential factor. Good, it's fine. All right, so let's get the other partial and then we compute the values. So partial of z with respect x, that equals to, okay, oh wait, no, with respect y. Now, see check how this is going to be different when differentiating with respect to y, because yes, even though we have a potential product between two functions, if we focus on the variable y, it's not a product of functions of functions of y. So in this case, x will be held constant, and this is going to be just a number, you know, like f of x equals to what is this? 2e to the 2 squared, which is 4x, something like this, right? It's going to be like differentiating this baby exponential function. All right, so let's find the derivative using a chain rule. So the derivative of an exponential times a constant is the exponential times the constant. By minute chain rule, now we need to multiply by the derivative of the exponent x squared y. But in this case, we differentiate with respect y. What's the derivative of y? Well, that's just 1 times its coefficient, which is x squared. Now reduce x cubed e to the x squared y. All right? So that is our partial derivative with respect y. No product rule this time. So now we will evaluate the partial derivatives. Well, let me show you. Let me show you the Jacobian notation first. In the next example, I'm going to change the notation to the Lagrangian notation, so you can see how it works for different notations. So number one. We're going to evaluate the partial derivative of z with respect x. We put a bar, and we simply write down the order pair 1, ln of 2. In a similar way that when you evaluated the derivative of y with respect x, you put a bar, x equals to 3. Say you want to evaluate the derivative at 3. Well, you would denote it this way with a bar and indicate the x value. Now, because we have a function of two variables, I'm not going to write x equals 1, y equals to ln of 2. The order pair is more than enough. All right? What do we do next? Simply substitute. So, e to the x, which is 1 squared, times ln of 2, times 1 plus 2 times 1 squared, times ln of 2. Okay, just substitute. I mean simplify. 1 squared is equal to 1. That's e to the ln of 2. 1 plus 2 ln of 2. But in this case, e and ln of 2 cancel out. That is 2 ln 2 times 1 plus 2 ln of 2. Final answer. All right? Actually, I think I'm going to need the space here. Okay, and lastly for this exercise, to wrap up the exercise, let's the partial derivative of z with respect y bar 1 ln of 2. So the function we differentiate earlier with respect to y, I mean what we got earlier with respect to y, just substitute x equals 1 and y equals ln of 2. Alright? Should be very straightforward. That is 1 cubed e to the 1 squared times ln of 2. That means 1 times e to the ln of 2, because 1 squared is also 1, I don't need to write that 1. And e to the ln of 2, they cancel out. And that's going to leave us with 1 times 2, which equals to 2. Right? So that is our partial derivatives with respect to two variables and how we evaluate the partial derivatives for a given point. Not anymore just an x value or just a y value. No, in this case it's both values at the same time. Again, so finding the derivative of a function, I'm going to repeat this, gives us the slope of the tangent line on a curve at a given point. So what is the value of the partial derivative of a given order pair? Well, in a similar way, well, the picture is on the next page. So the function f of x, y, is not going to give us a curve. It's going to give us, or it's going to represent a surface. The point we evaluate the derivative at, it's going to give us, well, I mean, the partial derivative evaluated at that point, well, depending on which variable are we differentiating with respect to. If we are differentiating with respect x, well, that's going to give us the slope of the tangent line that is parallel to the x-axis. That is the slope in the x direction to make it easier to visualize. And the value of the partial derivative with respect to y at a given order pair, it's going to give us the slope of the tangent line to a surface that it's parallel to the y-axis. In other words, it's going to give us the slope in the y direction. All right. Well, so that's what the partial derivatives mean. Slope in the x direction, slope in the y direction. But actually, what about the slope in other directions? Because I mean, think about the real world. We don't just move in the x and the y direction. Yes, we describe locations and points as coordinates x, y, but when we move in many other directions. Maybe in the direction 30 degrees, 45 degrees, in the direction of a vector, for instance. Well, that's going to be another derivative that we will discuss later, which is called the directional derivative. But that's going to be later. All right. For now, let's keep practicing with finding partial derivatives. Well, let's do another partial derivative. That is, find the slope in the y direction for the surface given by f of x y equals to sine squared of x minus 3y. So now we have another composite function, you know. So it would be better actually if you write it in this form. All right? That way it's easier for you to see the chain rule. All right? Can you pause? All right, so let's see. So partial, and in this case they're only asking us for the slope in the y direction, not the slope in the x direction. So that means we will only compute the partial derivative with respect to y. All right? So, and I'm going to change the notation, by the way. This time I'm going to use f subscript y. So that is because in this case we're not given z, we're using the f notation. Okay, 2 sine of x minus 3y. So that's the derivative of the exponent of the sorry. So that's the utmost. So now let's differentiate the second function, that is the derivative of sine. That'll be cosine of x minus 3y times the derivative of negative x minus 3y with respect y, that'll be -3. Right? That's our chain rule here in action for a function of two variables. So let's simplify this. That equals -6 sine x minus 3y cosine x minus 3y. All right? So we have the derivative. Now let's evaluate the derivative at the given point. Now be careful. Don't freak out if you are seeing an order triple. In the previous exercise, we were given an order pair to find out what the value be. Well, actually, we didn't need the z value because we were not looking at the c value. We were looking at the value of the slope. So that means, so this z value is the f value, the function value, when you substitute x equals to pi over 3 and y equals to pi over 6. Okay, so so let's evaluate the derivative at pi over 3, pi over 6. Oh, just these two is fine. 2 sine of x, which is pi over 3, minus 3 times, 3 times pi over 6 cosine of, it's minus 6 rather, -6, cosine of pi over 3 minus 3 pi over 6. Okay, let's simplify the quantity inside of the parentheses. Okay, that is, this 3 pi over 6 will reduce to, what's that? Well, actually, it would be better if I multiply by 2 to get all denominators 6. So that'll be, in essence, 2 pi over 6 minus 3 pi over 6. Isn't that negative pi over 6? So let me change this to all negative pi over 6. Negative pi over 6. Negative pi over 6. So -6 sine of negative pi over 6 cosine negative pi over 6. Okay? And well, before we compute these quantities, if you don't want to deal with negative angles, just use the even and odd properties of trigonometric functions. Recall that sign of a negative angle, the negative goes outside. While cosine of a negative angle, the negative just disappears. That's because, number one, in the first case, sine of a negative angle, the negative goes outside. That's because the sine function is an odd function, while the cosine function is an even function. So that means, so if this negative just goes outside, get to multiply with the negative to become a positive. Sine pi over 6, cosine pi over 6. Okay, so what is this? 6 times 1/2 root of 3 over 2. So this will be 6 over 2, that's 3. 3 root of 3 over 2. So that is the value of the slope for the surface at the point pi over 3, pi over 6, 1/4.